So here, pre-lab question one, we have some hypothesis given to us. So the null hypothesis is mu is equal to 1,000, and the alternative is mu is greater than 1,000, meaning that this is an upper-tailed test. We're also told that the standard deviation, that would be the population standard deviation here, is 70, and that the sample size is 49. So we're asked to draw the distribution out. So I guess the first thing that we need to ask ourselves is, what distribution is this? And here, because we do know what population standard deviation is, the sigma, that means that this distribution is a z, or a normal distribution. Okay, so here then, if we are going to divide, so here we're trying to see if something is significantly bigger because the sign is the greater than sign. So if we're going to allow 5% error, that's type 1 error. 5% error would be here. The type of error would be rejecting the null hypothesis, even though the hypothesis is true. So that would be a type 1 error. So that is called alpha. Okay, so what that means is, if the null hypothesis is true, then that means that this distribution, which is the z distribution, is actually centered at 1,000, where the standard deviation is 70. And we would reject that here 5% of the time. We would reject it even though it really is 1,000 5% of the time, which really will give us here this value, this line in the sand where we reject versus where we fail to reject the null hypothesis, which is called the critical value. So if we want to find the critical value here, what number is big enough so that it looks like 1,000 is not actually what the number is? So what number is big enough that all of a sudden it looks like it makes 1,000 look small? And so we can find that by using the distribution that we know here, which is normally just normal distribution, and the center being 1,000, the spread being 70, and the sample size being 49. So here, if I want to find this critical value, on the right I know that there's 5%, which means on the left I know that there's 95%. So I can use the command qnorm of 95%, that's the area on the left, where the middle is 1,000, and the spread of this distribution is 70 divided by root 49. So when I do that, I get that value to be 1,016.449. Okay, so here, this is talking about x's, or data in context. So here, the number 1,016.449, or anything bigger than that, is now appearing to be significantly bigger than the number 1,000. Of course, you could get this into standardized notation, or z-scores, if instead of doing qnorm of 0.95, where the middle is 0, where the middle is 1,000 and the spread is 70 over root 49, you could say, what about if I've got 95% on the left, where the middle is 0 and the spread is 1? That's standard normal here. So when you're talking about z-scores, the z critical value is 1.644854. And here, the x-bar critical value, which is really the same point, but just talking about in terms of x-bars, what is a rejection and what is not. Okay, so we can have critical values either in terms of x's, or x-bars here, or in terms of z. So what that means is we can determine decision rule. What this means is, if your sample mean is bigger than this value in terms of x's, which is 1,016, then you would reject the null hypothesis. You'd say, no, it looks like its number is significantly bigger than the number 1,000. And if you are making test statistics in standard form, that is, you are using this formula, or getting the test statistic, then instead of using the number 1,016.449 for the critical value, you would use the critical value in terms of standard z-scores, which would be 1.644. So if your x-bar is bigger than this number, you'd reject, but if your test statistic was bigger than this number, that's where you would reject. So here, what does this question continue to say? It asks us here, then, if we did collect a sample and the sample's average was 1,006.26, then what would we do? Okay, so over here we said that if sample's average was bigger than 1,016.44, we would reject. But in this case, our sample's average is not. It is 1006.26, which is smaller than this 1016. So here's 1000, here's 1016. Our number 1006 is somewhere on here. You can see that it is not in the rejection window here. The other thing you could have done with it was to actually make a test statistic. So here, if x bar was the number that they say, then we could use this formula to find the test statistic in terms of z-scores. So here, 1006.26, subtract 1000 over 70 and divided by root 49, I got the number 0.626. Okay, so this number would be on the z scale. So here we would use this z standard scale critical value, and you could see that 0.626 is actually on the left as well. So both if you're looking at X bar versus X bar critical or test statistic versus Z critical, you would not be in the rejection region, so you would fail to reject. The other thing that you can do, of course, is to find the p-value. Okay, so what is the p-value? Again, the p-value is the tail probability of the test statistics. So if we found the test statistic here, and then if we had plotted it on our plot here, it'd be somewhere around here, and the p-value is always the tail probability. Which tail is it? It's always the tail that's indicated to you in the alternative hypothesis. So this is a greater than test, which means the p-value would be on the greater than side of the test statistic. So I could find the p-value in a number of ways. One would be to say, here's the p-value probability statement. We are recognizing that this distribution is the z distribution. Then the test statistic with respect to the z distribution here is a standard z score of 0.626. And here the greater than sign is telling us which side of the test statistic the p-value is on, which in this case would be the upper tail or the right side. So if I was going to calculate that in R, I could find here the probability being on the right side by being 1 minus the left side. So 1 minus the probability of being on the left side gets me the p-value. Okay, there are a number of ways to do those things as well if you were so inclined to use zsum.test if you like, or just with this method. So that is the p-value. In this case, if the p-value is greater than alpha, we would fail to reject. And when the p-value is less than alpha, we would reject the null hypothesis. In this case, our p-value is somewhere around 27-ish%, and our alpha value is 5%. Therefore, with all three ways, either using either decision rule or the p-value, our x bar is, in fact, smaller than X bar critical. Our test statistic is smaller than Z critical, and our p-value is bigger than alpha. All three of those things suggest the same idea, which is that we need to fail to reject the null hypothesis, which means that the number 1006.26 is not significantly bigger than 1000. It isn't big enough for us to say for sure that this is a bigger number. Okay, let's remind ourselves what p-value means in context. Again, sort of the blanket statement is that if the null hypothesis is true, then the probability of observing more evidence against the null hypothesis is the p-value. Specifically here, if the null hypothesis is true, what's the null hypothesis? The null hypothesis is if mu is 1000. So if the center really is 1000, then the probability of observing more evidence against the null hypothesis, in this case, more evidence would be here greater values than the null hypothesis. So here that's talking about the right tail. So the probability being on the right of the test statistic would be here the p-value. Okay, in this case, the p-value is high. What does that mean? When the p-value is high, so remember here, the probability of the p-value is on the right side. So if the probability of this right tail is big, what that means is the test statistic is getting closer and closer to being what the hypothesized value is. So here you can see when p-value is high, so when I'm coming from the right tail into the center, when that's high, I'm getting closer and closer to what the null hypothesis, which is in the center of the curve, is. So here, when p-values are high, really what that means is this is actually likely to happen. So what that means is we're actually close to seeing what we thought we were going to see. We're asked to describe what type 2 error is. So generally speaking, type 2 error would be failing to reject the null hypothesis when it's false. In this case, what would failing to reject the null hypothesis be? Here's the null hypothesis. If we fail to reject that, then I guess we would believe that mu really is 1,000. So here, type 2 error would be thinking that mu is 1,000 when it's actually not, okay? When the null hypothesis is not actually correct. Okay, continuing on, let's see. So we just said what error could we have made? The error we could have made if we were failing to reject. So all of these things said that we should fail to reject. The only error that we could make if we were failing to reject is a type 2 error. The only error you could make if you were rejecting the null hypothesis is a type 1 error. And then just drawing this out again, here, suppose that the actual mean was 1,020. So we assumed the actual mean was 1,000. When we sampled, we found the sample mean to be 1,006.26, but perhaps we thought it was 1,000, and then we set up our decision rule, which was that if X bar was actually bigger than 1,016.449, we would reject the null hypothesis. And but now we're saying, what if the truth really was that mu was 1,020? Okay, so here we've got two separate curves. One curve is based on the null hypothesis, that is, that it is centered at the number that we had in the null hypothesis. And now a second curve that's saying, well, what if the truth was really 1,020? So another curve that is based on the center actually being 1020. Okay, so here on our null hypothesis, this is really what defines our decision rule. So we've already defined when we would reject the null hypothesis if the middle was 1,000. And so we've already defined when we would reject the null hypothesis. And so we could draw a new curve saying, well, on this side of 1016.449, we would reject the null hypothesis. But what if the curve was actually centered at the value 1020? Okay, so here, if the actual curve was centered at 1020, what is the probability that you would conclude that the mean is equal to 1000? So you have to think about this in context. What would be the probability of thinking that mu is 1000 given mu is actually 1020? Okay, so this part of the statement, thinking mu is 1000 or concluding that the mean is 1000, another way of saying that is when looking at the null hypothesis, if we think that mu is actually 1000, what that means is we failed to reject that. We actually believe that that's true. Okay, so here this part would convert into failing to reject the null hypothesis, and then this part would convert here. Here, if mu is actually 1020, then that means it is not 1000. And another way of saying mu is not 1000 is to say that the null hypothesis is actually false. So here, this statement that says what's the probability of concluding that the mean is actually 1000 when in fact it's actually 1020 is another way of saying what's the probability of this case failing to reject the null hypothesis when it's false, which is called a type 2 error. Okay, in this case, type 2 error would be beta. Okay, so what they are actually looking for then is the probability that you would fail to reject the null hypothesis. Okay, so here, if you're looking at the critical value, failing to reject the null hypothesis is on the left side of the critical value. And then they're saying, what's the probability of failing to reject the null hypothesis if you are talking about the curve that's actually centered at 1020, not the curve that is centered at 1000. Okay, so this right here, this is the area that they're looking for. So here, how do I do that? I'm looking for the area on the left, okay, that is beta, that is the probability of type 2 error, that is p norm of this critical value, where the center of the curve is not 1000, but 1020, and where the spread of the curve is sigma over root n. So that would be 70 divided by root 49. And then I finally calculate here, this is the probability of making the type 2 error that they are explaining here in this statement.